Hello, my name is Zhe from Harvard. It's a joint work with Chara Podimata and also Vasilis Syrgkanis from Microsoft Research. So actually they are both here. Okay, so let me first do a quick warm-up for the standard auction design. That is like we assume we have several bidders in this auction, and each bidder has a private information. So we call VI, which is a private valuation. And each bidder will submit a bid to the auctioneer, and the auctioneer will decide which bidder wins the item and how much the winner need to pay. So we call the allocation rule and payment rule. And also we always assume like each bidder has a utility function, and usually it's modeled by a causal linear function. Okay, so actually in the standard auction theory or mechanism design, there's a key assumption that is the bidder know his true valuation before submitting the bid. So here we want to argue this assumption. So for suppose we consider a small market, and suppose the bidder have enough time to prepare to bid, like they can do some market research. So this assumption somehow makes sense. But suppose we consider an online advertisement auctions, and the bidder has no enough time to prepare, and or even they don't have information about their valuation. So this assumption somehow doesn't make sense. Okay, so this thinking motivates our main question in this paper. So we want to so our question is like, can we design a bidding strategy for the learner in the online advertisement auction to when this learner doesn't know his valuation before submitting the bid? So actually, our work is also motivated by the sponsored search example. So let's consider a learner or the advertiser in this sponsored search auction. And this learner will submit a bid to the platform, and the platform will generate the allocation rule and payment rule. So here, the allocation rule can be regarded as the click-through rate, and payment rule just the expected payment per click. Okay, so suppose this learner wins a slot, and this slot is clicked by some users. So, and the learner can observe some valuation. So here's a valuation, also the expected valuation. And so now I want to emphasize the main assumption in our model. That is, no matter what happens in here, so no matter what, so whether the learner wins the slot or whether the slot is clicked, the learner can always observe the allocation rule and payment rule. So why we have this assumption? That is because, for example, in Google, they provide so-called a bid simulator to help the bidder to estimate their allocation rule and payment rule. Okay, so given this information, both the learner can observe the reward, which is value minus your payment. And since this reward happens with the probability xt, so the expected utility is equal to value minus payment times this probability. So actually, we can use a very simple model to capture this previous little complicated example. So that is, so here we focus on the single item auction. So every day, the learner, the designer and a competitor will choose the allocation rule and payment rule. And learner will submit a bid from a finite site, okay? And the learner wins this item with the probability xt here. And at the end, the learner will observe the allocation rule and payment rule. And if the learner wins this item, he will observe also observe the valuation. And given this information, the learner can estimate his expected utility function in this formula. So the goal of this learning task is to minimize the expected regret in this formula. So here the UTB star is a utility with best fixed bid in inside. And UTBT is a utility with a bid generated by this learning algorithm. So actually, this is a special case of a multi-element bandit problem. So what is multi-element bandit problem? That is every day or every round, the adversary will choose a reward vector. So each element in this reward vector corresponds to the reward for each action. And the learner will choose the action from a finite site. And learner can also get a reward for this specific action, for this specific arm. And and the learner can only observe this reward. So this setting called a fully bandit feedback setting. And there's a celebrated algorithm called EC'18 algorithm can achieve regret equal to square root t times b. Okay. So given this thinking, so since in our auction setting, we have the learner has more information rather than just the fully bandit feedback. So we can formally define our main question here. That is, can we design an online learning algorithm for the learner to achieve better regret than the generic multi-arm bandit algorithm, like EC'18 algorithm? So our main results is we design a so-called win-ESP algorithm. So we utilize the partial feedback information from the auctions, and we can achieve better regret bounds than the generic multi-arm bandit problem. And so actually our regret bound is similar to the full information feedback regret. Okay, so there are lots of related works here. There are a lot of papers talking about how to maximize revenue from the auctioneer side. But from bidder side, there are only few papers. So Dikle and Tardosh, they first think about, suppose the bidder don't know his true valuation before submitting a bid. And the auctioneer, so in their paper, the auctioneer can put some initial credit to incentivize the bidder to do some experiment to discover their true valuation. So at the end, the auctioneer and bidder will both benefit from it. And the most related work is from Wade et al. In 2016. So they consider the repeated second price auction. And actually, our work is a generalization of their work. We propose a simpler mechanism which can recover their regret bound for the repeated second price auction. And we can easily extend our work to handle more complicated settings like sponsor search, generalized second price auction. Okay, and also work is closely related to contextual bandit literature and feedback graph literature. Okay, so now I will move to more technical parts. I will introduce our algorithm formally, give some proof sketch, and show the extensions and applications. Okay, so actually we can do an abstraction of our price model. So we call this abstraction the win-only feedback framework. So that is every day the learner will choose a action from finite side B, and the adversary will choose the reward. So here the reward corresponds the valuation minus payment in previous model. And also the adversary will choose the allocation function. So the learner will win the reward with the probability xt, which is allocation probability. And so in this model, the feedback is the learner can always learn the allocation rule xt. And suppose he wins, he will also learn the reward function. Okay. So our win-ESP algorithm for this feedback is as follows. So every day, the learner will draw a bid from a distribution pi t, and he will observe the allocation rule xt. And suppose this learner wins, he also observes the reward function. And give this information, the learner can compute so-called the unbiased estimator of this utility function minus 1. So if the learner wins, this unbiased estimator U tilde TB is equal to this formula. So actually here the XTB is the winning probability conditional on the suppose your bid is equal to B. And the denominator is the total winning probability given this distribution pi t. Okay. And similarly, if a learner doesn't win, he can also estimate this term. And at the end of the day, the learner will update his distribution pi t using the exponentially update way. Okay, so the proof sketch. So firstly, we know like the regret with ut is equal to the regret with ut minus 1. Okay, it's very simple. And as I mentioned before, so since utb is the unbiased estimator of ut minus 1, and since this ut tilde is always non-positive, and so we can apply this lemma here, lemma 1 here. And so the key point in our proof is how to bound this variance of estimator. So in our WinESP algorithm, this can be bounded by a constant number, which is 5 in this setting. But suppose we use ESP3, this term will grow as a number of actions. So that's why our algorithm is better than ESP3. So currently, so everything is good for, like, suppose we only have two outcomes, that is win or not win. But actually, in a lot of different auction settings, there are multiple outcome cases. So actually, we can generate our setting to handle this multiple outcome case. So we call the outcome-based feedback setting. So the difference, like the reward function now not only depends on the bid, but also depends on outcome. And every day, a outcome will be chosen based on the distribution, xt. And the learner will win the reward. So, and the feedback here is like the learner will always observe the allocation rule and also the reward function for this specific outcome, OT. And our algorithm can also apply to this setting. So we can achieve a regret only linearly depend on the number of outcomes. And so in a lot of auction setting, we will see later, so this number of O is very small. So okay, let's see some applications here. So firstly is a binary outcome case. So actually second price auction is a very good example. There are only two outcomes, win or not win. And suppose we use the discretization properly, we can exactly recover without our results. And also the value per click auction is also a binary outcome case. And for the non-binary outcome case, imagine a unit demand k items auctions. So since the bidder can only win one item each time, so there are totally k plus 1 outcomes. So so we can also easily apply our setting here. Okay, so now currently we only talk about suppose the bidder submits a bid from a finite site or the discrete bidding space. But actually, the bidder can also submit their bid from a continuous action space. So imagine a continuous interval. And so now we generate our setting to handle the continuous action space with piecewise Lipschitz rewards setting. So now I would not give a formal definition of what is piecewise Lipschitz rewards, but high level speaking, like let's consider a single dimension setting, and we have several intervals of this bid space, and in each interval, the reward function is the Lipschitz function. And here we denote the delta 0 is the length of the minimal interval, okay? And here L is the Lipschitz constant. So, and when we apply our algorithm, we can achieve regret by replacing the number of actions B to this red term. Only depends on delta 0 and LT. And actually, there are also several applications here. Second price auction and also first price auction and all pay auctions. And we can also utilize apply our setting to handle weighted GSP auction setting. That is, each bidder is assigned a score drawn from an auctioneer, and we allocate this slots using this decreasing order of weighted scores, and the bidder will be charged the critical value. And suppose we assume this score is generated by a distribution with Lipschitz CDF, we can show this utility function is Lipschitz. Okay, so we run some simulation here. We consider 3 different opponents' behaviors. That is stochastic, EXP3, and also win ESP. So which means like for the stochastic setting, the opponents will submit their bid ID drawn from some distribution. And ESP3 is like the opponents will submit bid by playing in the ESP3 algorithm. And similar for the WinESP. So, and we consider different discretizations here. And we can show our algorithm always perform better than the ESP3 algorithm for different discretization. And our algorithm is robust with a different discretization, but ESP3 is not. And here we assume the bidder can get the exactly perfect allocation rule. But suppose bidder gets some noisy allocation rule, what happens? And we run some simulation to add a Gaussian noise in this CTR estimation. And our algorithm also performs better than ESP3, but suppose the noise is very large, this improvement is limited. And it holds for different behavior setting. And it's a final simulation. And so now we come back to consider the fully banded setting. Suppose the bidder don't know the allocation rule, but he can observe the fully banded, which is just the allocation and payment if he win. But he can use this information, the previous information, to estimate the allocation rule and payment rule, and use this estimated allocation rule and payment rule to run our algorithm. And our algorithm can still perform better. So somehow, our algorithm is robust to the fully banded setting. And so this is, in summary, we design a new algorithm called the WinESP3. So we utilize a partial feedback to achieve better regret. And we can apply it to a lot of different auction settings. And our algorithm has robust experimental performance. OK, that's it. Thank you.